Hello, my name is Frudu Bhatti, and this is a lecture on classification and model evaluation for Data 630. In this lecture, we will cover some of the basics of classification such as function estimation, probability prediction, categorical prediction, and we move on to model performance such as how to evaluate models, how to capture some of the metrics using confusion matrix, and the actual evaluation matrix, and one of the popular performance charts, ROC curve, and the corresponding metric, which is area under the ROC curve. Okay, classification basics. Classification is a type of supervised learning where you have annotated training data set and you apply a learning algorithm for estimating the data generating process. Okay. So the key in supervised learning is you have to have labeled manually annotated target variables we call training set, and you apply. So the assumption in classification setting in general in supervised setting is there is a data generating process as a result of which you see the observation that you see. The data was generated from a domain, so some kind of data generating process. So there is a function responsible for the data generating process, but we don't have access to that function. So we have to make an estimation. So the trained model is an estimation of the function, that function. Okay? And the estimation is a kind of generalization because we have a set of observation which is a specific case, and we try to generalize it from that specific cases. So that's classification. The key difference between classification and regression, which both are type of supervised learning, is in the case of regression, which we covered in the last module, it's just linear regression. The outcome variable or the target variable is a continuous value, okay, numerical value. In the case of classification, they have categorical value, which with discrete number of outcomes. So the prediction or the classification involves predicting those outcomes. In general, most classifications are binary outcome. That's like 1 or 0 or yes or no type of problems, binomial distribution. But you can apply multiple binary for problems involving multi-class problems. So although some of the latest algorithm can directly handle multi-class problems, the easy and the simplest application is you use multiple binary outcome or binary classifiers to handle multi-category problems. Okay, so like I said, there is a function that's responsible for the data generating process. Now we apply some kind of algorithm, and in this module we will be learning about the decision tree algorithm, which is one type of classification learning algorithm. But it could be anything, right? You apply that algorithm on the observation on the training data to estimate the function. So the trained model is function estimation. And so basically it is a mapping, that function is a mapping between the characters, the variables, the explanatory variables or attributes to one of the predictor class labels, which is a Y. Okay. So each record is basically for the classification process, each record that is a tuple, a combination of the X and the Y's is our input, right? Set of observation. Now the X's are obviously vector involving multiple variables, and the Y is the scalar function. Okay, now the learning algorithm. So, like I said, the principle, the general approach is for estimating a function, but that function estimation can be handled through different algorithms depending on the data, depending on the assumption, and a lot of other things. In the performance of the learning algorithm for a given data set you may apply different algorithms. So that is the relevance of the algorithm. The application is the same when estimating a function, but you apply different kind of learning algorithm and techniques in different circumstances. So so examples of this classification, at least the commonly used learning algorithms, are decision trees. Although a variant of decision tree that combines multiple decision trees is the most commonly used one in production environment, that involves like gradient boosting or random forest type of learning, which we will not cover in this course, but you will learn it in the next course, Data 630. So that is one application, neural network, and it is newer application which is called deep learning. Is also another type. Now, support vector machine is another one. All the three can be also used for regression applications, where the outcome or the target variable is a continuous variable. Naive Bayes is another type, simplistic approach, which we covered in module 2 in logistic regression, which applies some of the assumptions of a linear regression, but the purpose is for predicting categories. Okay, so how do we apply, what is the application context for classification technique, and in general for supervised learning? Now, there are primarily two types. And this was the case when we discussed about linear regression as well. Now, the main difference between classical techniques like regression and modern algorithms like machine learning is in the set of assumption that we make. We tend to make less assumption in machine learning, but in classical or traditional technique like linear regression, there are a set of assumptions. You know, some of the assumptions that we discussed in module 2. Now here, again, this applies for both the classical techniques and latest algorithms. One is prediction. The focus is for predicting the outcome of the target variable. In the case of classification, the categories. In the case of regression, the numerical value of the outcome. That's prediction, without focusing or emphasis on the underlying relationship between the variables, the predictors, and the target variable. And another common application is for inference purposes or advice, which means you're not only interested in the prediction of the target variable, but you want to understand the intricacies and the detailed relationship between the variables and the target variable. Okay, that is inference. Now, typically, classical techniques like regression are primarily used for inference algorithms, but modern algorithms, mainly because active involvement of statisticians and mathematicians and machine learning approaches, because of their interest in applying machine learning and by combining with a statistical inference technique. Now, some of the latest machine learning technologies can also be used for inference purposes. For instance, if in random forest or gradient boosting algorithms, you can directly identify the ranking or the importance of the explanatory variables based on their influence or their relationship to the target variable. Okay, so those are the two primary uses of classification and or supervised learning. Okay, this is a good summary about, in general, how the fitting process of a supervised learning or a classification algorithm. So like we said, the start point is you have a data set from a given domain, right? It was generated with assumptions. The assumption is that data was generated through some kind of data generating process. You know, there is a function responsible for generating that data set. Okay. Now we try to estimate that function based on the observation that we have. This is X here in this diagram. So this is our main input. And we have, for each of the corresponding X values, there is annotation for the variable, the target variable Y. So we apply some kind of learning algorithm. Like I said, could be decision trees, could be neural network, support vector machine, any of the variants of there are many algorithms that, and then the selection of the algorithm is a function of many things: application, to what extent the accuracy has to be, and the type of data and set of assumptions. So it's a number of things. There are a number of things that dictate the selection of the appropriate algorithm. But you apply a learning algorithm, then you apply on learning algorithm in the data set, and you estimate that function. And that is your trained model. So at that point, you have a model. And now how you use the model is for future cases. Now you don't have label data, right? In the case of prediction, if you want to make a prediction, you apply this model for future cases that doesn't have any label, and that would be the output. The prediction of the category of that class or that target variable will be the application of the model, right? So that is what is involved in general in learning, training a learning model or training a classification model. So again, the key takeaway from this is for supervised learning, there is a training data that has annotated labels, and you apply a learning algorithm for estimating a function that generated the data that you have, or the observation you have. Now, part of the things that we will discuss is part of this training, or part of applying the learning algorithm involves also evaluating the performance of the model. So, and in general, you don't evaluate the performance of the model on the same trained data that is used to train the model. So you need to set aside a test, hold out the sample or test case as you train the model to also evaluate the performance of the model, which will be the second part of this lecture. We'll focus how you do evaluation, both in the training and the test, and how to compare those things. And again, there are various algorithms. The focus on this module will be decision tree algorithm, simple decision tree algorithm. In the next course in Data 630, you will be learning the more advanced application ensemble trees, such as gradient boosting and random forest. Okay, so classification output. What is the output of classification? Primarily, there are two. Now, remember, the application is still classification. The purpose is for categorizing outcome, but the output can be continuous value, which is a probability value, or a discrete category. So, for instance, if you think about one application for a spam detection. So if you are training a model for spam detection, one potential output would be the probability of any given email is a spam. Okay, that's a probability outcome. Now that probability outcome could be any number ranging from 0 to 1. And you pick a threshold value. By default is 50. Anything above 50 would be categorized at the positive case. In this case, a spam email, the email is spam. Now, there is a range of values, as you can imagine. Now, in this case, I'm showing here the output. For instance, if you train two different models, if you apply two different learning algorithms for spam detection and fit a model, for the same case, if one identifies 0.51 probability and another one 0.95, in terms of discrete outcome, they are both the same. You are categorizing the email as spam. But in terms of confidence, you will have more confidence in the model that identified that email as with a 95% probability. Okay, so and when we discuss about model performance, we will get into how you can leverage this continuous value, continuum scale of probabilities for optimizing some of the evaluation metrics that we will discuss later. But for decision making, probability is less useful. So you have to convert the probability number using some threshold and actually convert to a crisp categorization, discrete, whether it's a spam or non-spam. Or this, or for instance, in the case of applying a fraud detection, for instance, is a transaction fraudulent or not fraudulent? Okay. An issue that is related to this is some algorithms like neural networks, they don't directly output probability values. Okay, probability has a set of requirements, a set of principles, like the sum of the probability of each outcome of the variable should add up to one. The distribution, if it is a probability mass function, there are a set of requirements to qualify as a probability. But some algorithms do not produce that. For instance, neural networks, the output can range from -1 to 1. Okay, so you have to do some kind of transformation. One that is commonly used for neural network is a softmax for deep learning, which is extension of a neural network, is a softmax transformation, which is here. So you have to take the exponent to the e to the estimated target, the prediction, and you normalize by the sum of that same quantity. Okay, and that will make it look like a probability. It's not a probability, but it would act like it would resemble some of the function, the characteristic of that output be like a probability. So it's a probability like number through a transformation. There are other transformation types. I'm just talking about softmax as an example, right? So you in some cases, but effectively for the purpose of outputting a continuous value, they're very useful. Model evaluation. So I can't emphasize this enough. It is a very critical aspect of model fitting or modeling in general. You have to apply appropriate metrics and evaluate the model through a number of scenarios to make sure the model will be performing as expected. Okay, and so I would say many new data scientists, they tend to not focus on this aspect of the problem. In the course introduction, I discussed about how much time you would spend in general on data preparation and understanding the problem, defining the problem before you do the actual modeling. And they say up to 70 to 80% of the time in modeling actually spent on data prep. The next exhaustive process is actually model training and model evaluation. In fact, you should consider that as part of the training. Evaluating the model is a critical aspect when you do performance, when you fit them in any kind of model. Okay. So one of the things that can be achieved by doing performance evaluation is you can safeguard against overfitting. And I will talk about overfitting, what overfitting is, and what overfitting issue might involve, right? And again, the one thing that you have to know about overfitting is if you have an overfit model, it doesn't generalize well. So future cases, you can't guarantee you will be getting the same level of performance that you see on the training data. Okay. Now, a very important aspect of model evaluation in general is using an independent sample that did not contribute to the training of the model. Okay. You have seen cases in the exercises that you have to separate the actual training set sample and a model evaluation sample called test. And that takes different variants. There is a cross-validation, which is a repeated sampling into multiple folders, and I will discuss that as well towards the end of this lecture. Okay, but the key takeaway from this slide is model evaluation is an integral part of training the model, and you have to spend enough time to make sure the model is evaluated. Okay, otherwise you might get the wrong confidence in the model, sense of confidence that it will perform based on the performance using on the training sample. Okay, let's move to overfitting issues. So overfitting, I kind of discussed about overfitting when we discussed about linear regression. But by the way, overfitting is not unique to any particular algorithm. The extent to which some algorithms are affected by overfitting issues are different. That's obvious. But most most algorithms suffer from overfitting unless you safeguard from overfitting issues. So what is overfitting? Overfitting is a scenario where you train in the interest of performing well for the prediction accuracy or whatever the case may be, whatever metric that you use. You work hard, the algorithm works hard to learn about the noise, the nitty-gritty of the training that is not representative in the sample that is not contributing for the training. Okay, so for that particular sample, the model is trained well, it performs really well, and whatever metrics you use, it's the optimum. But that might not be the case for the future cases that you haven't seen yet. Okay, so overfitting, if you overfit, the generalization of the model will not be good. Okay, so one way to safeguard against that is, as part of the training, you also evaluate the model performance, again, regardless of the type of metric that you use, to also test it on an independent test. Okay, here I am showing a plot of the performance of this is actually a model that I fit in production using a gradient boosting, one of the ensemble techniques that you will be learning in Data 640. So the vertical axis is the square loss. That's a metric that we try to optimize here to minimize it. Okay, and the vertical is the number of trees in ensemble tree that are being added in a way, so the extent to which the model's complexity is increasing. So as you go further to the right, that's the number of trees that are being added to the model. Okay, now the black line right here that you see is the error, this square loss error on the training sample, on the sample that is contributing to the training of the model, to the fitting process. As you can see, it will continuously going down. So as the complexity of the model is increasing, as we add more trees, the training error is going up. And that's always the case. As you add complexity to the model, the performance of the model for that training, that unique training sample, is getting better. But at some point, you are actually learning the noise in the data, and you're not generalizing. The model is not generalizing well. And now here, I have two separate lines on independent sample. That means it's a sample that is not actually being used in the training. The green one here, I'm showing typically you don't have to use two independent different separate sets. Here, as a function of the learning algorithm, there is one separate testing called boosting. Boosting is a sampling technique with replacement. So multiple bootstraps, you take multiple bootstrap sample. So this blue one is that sample. The other one is a cross validation that I haven't discussed what cross validation is. I will discuss that later in the slides. But the key is, regardless of what kind of sampling you use, is you are actually also performing as part of the training the performance of the model on an independent set. Okay, so here, as you can see, at some point, even though the training sample continuously going down, you don't see that decrease in the error in the independent set. That means you starting overfitting the model. You are learning about noise in the data, not a general trend that you can leverage for future cases. So that means for this particular model, anything above this number of trees or anything beyond this complexity of the model is a boundary condition where you start overfitting. Okay, in both cases, in the bootstrap case, again, you don't have to use different samples. Cross validation might be sufficient here, but both tell the same story. Here, a little too optimistic. It is showing you that the actual overfitting is starting right here. And in fact, it's getting worse. the error on the bootstrap sample, which is an independent set that's not contributing to the training, is actually going up while the training error is going down. Here it is more or less, you're not getting improvement on the independent sample, but you're not getting improvement either. So this is an area where overfitting has started, and you have to terminate. You don't learn beyond that. You don't add complexity to the model beyond that point. So this is one common technique that is used for preventing overfitting issues. Now, there are some advanced learning algorithms that actually directly handle overfitting through regularization. What it means is, as part of optimizing the function, there is a term that continuously safeguard against overfitting. It's a different technique, but this is the most commonly used way of avoiding overfitting. Have an independent set and make sure, as part of the training, evaluate the model, how it performs on an independent set, and stop adding complexity to the model when you get to the point where actually you start performing worse on the part of the data that is not contributing to the training. So that's overfitting. Okay, now we move to other aspects of model evaluation, right? There are a number of metrics. Now, again, as you progress in the field, when you apply different learning algorithms, some advanced thing, the ensemble training, so the complexity of the parameters also increase. I'm talking about the performance evaluation parameters or metric. Here we will be looking at simple metrics like accuracy, precision, and sensitivity. So confusion matrix is a way to capture the predictions in the actual in a tabulated. It's just cross tabulation of classifier prediction against the actual. Here I found this nice picture that captures different cases here. So here now you see that in some cases the actual target on the horizontal and the model prediction on the vertical. Here in this particular one, the vertical ones, the columns show the actual cases in the data. It's called target here. Here is a predicted case, a prediction from the model. So this is a binary case. You have a positive and negative samples, regardless of what kind of an application. So the positive means is the class of interest. Okay, in the case of email spam identification, the class of interest would be the category that the email is a spam, right? Okay. Other application, for instance, fraud detection, for instance. So the detecting whether transaction is fraud would be the class of interest. So that would be a positive class. So here the cells in the confusion matrix are the number of cases in each cell. For instance, A in this case is the number of correctly predicted by the class as positive, and they're also positive in the prediction. Here this cell shows this is the model predicted as positive, but actually it's a negative, right, in the data. So this is false positive as a model, positive. And here see the model predicts as a negative, but actually positive. That means false negative here. And here true negative. So that means the model predicted negative and the actual is also negative. So in general, the numbers on the diagonal of the confusion matrix are the correct prediction, and of the diagonal elements are wrong prediction. So your objective is to maximize the number of cases that captures in the diagonal higher and minimize the numbers of diagonal elements. Now you can see the vertical sensitivity, how the sensitivity is calculated, the specificity in the positive predictive values and negative predictive values, and overall accuracy. We will discuss all those parameters in subsequent slides. But take the confusion matrix is a very common tool, tabulation strategy for capturing classification performance, prediction, and actual outcomes. Okay, accuracy. This is a very simple metric which try to identify the proportion of correct prediction by the model. So basically you sum all the elements in the diagonal of the confusion and divided by the number of total cases. Remember, anything on the diagonal is a correct prediction or true prediction. So you add up both the true positive and the true negative prediction of the model and divided by the total cases you have in the, if you're evaluating in the training, the number of cases in the training. If you're evaluating the test case, then you'll be on the test case. But like I said before, to avoid overfitting, always you have to compare the performance of the training with the test. So you have to calculate both the accuracy on both samples. And again, it's a simple measure. For a classifier, accuracy is defined like this. But here is the issue with accuracy. Accuracy works relatively fine if the data is balanced data. That means if you have relatively equal number of cases from each class, each outcome of the target variable, right? If the distribution is balanced, the frequency distribution is balanced, then accuracy can fairly, capture the performance of the model, right? By the way, another way of tooling accuracy is error, right? If you are interested in measuring error, it's the same thing. 1 minus the accuracy will give you the error. Okay, they're all the same thing. But if your data is unbalanced, that means there are some outcomes of the class whose distribution are small, their frequency of cases, and then particularly when you have rare events that doesn't happen quite commonly at the rest of the outcome in the class, then accuracy is not a good measure. Also, depending on the application, you might be interested in one of the events. The event of interest, for instance, in the spam classification, you might tolerate some spams in the interest of not missing good emails, right? So you might emphasize some aspect of the model prediction than another, right? That's when we get into positive prediction, negative prediction. That will be captured. We'll discuss those metrics that will help you identify those kind of performances in the next slide. But accuracy will not be appropriate in that kind of, if you're interested a better performance in one of the classes than the other, then accuracy is not the way to go. Okay, that means it does not account or it doesn't make any distinction about the type of error. Type of error like type 1 error, type 2 error, like false negative, false positive. Okay, but accuracy can be a simple measure. It's easy to use, particularly when you have balanced data. So a little better one than accuracy that also takes into consideration the possibility that the prediction performance that you see from the model might be as a result of a chance. So it takes that aspect into consideration. It's called kappa statistic, which is calculated like this. You take the difference of the actual. So first of all, it measures to the extent to the degree to which the predicted and the actual are in agreement, right? That's what it measures. But it takes into consideration the fact that there is a possibility some of the prediction are done by chance. So number of n is number of cases, n is number of agreement. That means the numbers on the diagonal from the confusion matrix. And this is on the marginal, the number of agreement due to chance you can find from the confusion matrix on the marginal of the table. So you take the difference of the two and divided by the difference of the total cases and the one due to chance, and that's the kappa statistic. So you can also calculate in terms of proportion instead of absolute count. So it is a better version of the accuracy, a little better version of the accuracy. It takes a value anywhere between -1 and 1. If it's 1 or -1, it's perfect agreement. -1 means a negative prediction, correct opposite disagreement. Perfect agreement, but on opposite side. 0 means there is no agreement. So anything that was predicted by the model was all false positive or false negative, right? no alignment or no agreement with the true cases. Now, if you have balanced problem, overall accuracy and kappa statistics are proportional. They tend to be close to each other when you have a balanced problem. That's what part of the reason why, if you have balanced cases, observational data set, then accuracy might be sufficient. Okay. The most common metric for classification accuracy in binary cases, which can also be extended for multi-class through multiple binary cases, is precision and recall. Okay. Precision is nothing but the proportion of the true prediction as a proportion of what is predicted by the model, right? So if this is a proportion of, let's say you have 100 cases predicted by the model, right? If 90 of that 100 prediction are correct prediction, that the precision is 90%. So it is simply the true prediction over the true positive over the true positive plus false positive, right? So you take this is a proportion of all the prediction by the model, right? Regardless of how many there is in the data. So this is how you calculate the precision. A companion to precision is called recall. That's a little different. So you can even see it from the denominator is now it's as a proportion. Prediction as a proportion is a proportion of how many cases you have in the data set. So the detection ability of the algorithm. So for instance, in the case of spam or not spam email, so the recall will tell you how many of or what is the proportion of the true cases, the spam email that the model was able to detect. Okay, that is recall. Okay, now depending on the application, depending on your tolerance, you might prefer precision over recall or the other way around, right? So there is a metric that combines the two called F1 score. It's nothing but it try to optimize both. Okay, and it's calculated as two times the product of the precision and the recall over the sum of the precision and recall, right? And when it is 1, when F1 score is 1, that's a perfect. That means you were able to optimize both the precision and the recall. When it is 0, both are worse. Okay, so a classifier that improves precision and recall by sacrificing the other will have a lower F1 score. So it's a way to combine the two. If you remember from our discussion on association mining, there was a metric that combines support and confidence lift, right? It tried to optimize the two, and that's basically the same thing here. F1 score combines precision and recall. Okay. Now, if you prefer sensitivity and specificity, for the most part, you don't really have to use both precision, recall, and sensitivity and specificity. In fact, sensitivity is exactly the same as recall. Okay, it is a proportion of the model prediction that is correct, right? Sensitivity means, and specificity is for the negative part. You see, what is the rate of the true negative of the model prediction? If the model, just to use the same example that I used for the positive, if the model, for instance, if the model predicts 100 cases that are not spam, and you take the true and the negative as a proportion of that 100, so it is a way to identify the true negative rate of the model. Okay. In general, if poor classifiers always score worse on one or the other, right? If the model is poor, if it's not an optimal model, it tends to have one of this metric worse than the other. Okay. Now, this is a variant of sensitivity and specificity slide. They are called positive predictive values and negative predictive values. Now, when you think about it, sensitivity and specificity, when you talk about the two metrics, they are conditional on knowing what class they are, what is, class of interest is. But in the context of prediction, future prediction, we don't have that reference, right? We can't talk about the conditional. It has to be an unconditional, which requires a metric called prevalence. For instance, in the application of spam and spam for email detection, the prevalence would be what is the probability, if you don't know anything for a given domain, if you know nothing else, what is the probability of getting a spam email? So that would be a prevalence. Okay. Now there is different ways of estimating it. Now in the Bayesian context, it is called a prior knowledge. And so the positive predictive value and the negative predictive value, take that into consideration in the calculation. So as you can see here in the formula, prevalence was directly represented here. Okay. But in practice, in general, people don't use predictive values, negative and positive predictive values for evaluating models, primarily because it's hard to know in general the prevalence. What is the unconditional probability or unconditional distribution of the class of interest? Okay, so but I think at least in R, most confusion metric function will produce that based on, so they calculate the prevalence from the data you have seen, which is a way to estimate it, and they calculate the both parameters, both metrics. But it's good for reference, but in general, the sensitivity, the previous one, the conditional ones are what most people use. Okay, so another aspect of this is different charts. Now we discussed different metrics, right? So precision, recall, sensitivity, specificity, predictive values, and negative predictive values. Now there are for the most part, corresponding charts that you can leverage, you can visualize and contrast those metrics. Now these are some of the charts. Receiving operating characteristics is the most common one, so that will be the one that I'll be discussing in this lecture. But there are others that you need to look at: sensitiveness, specificity chart, lift chart, precision recall chart. Those are other charts that you can, as part of the modeling evaluation, that you can consider or leverage. But ROC curve is the most common one, which is which combines true positive rate and false positive rate. And we will discuss about ROC curves now. So like I said, it is a way to combine sensitivity with a specificity. So basically a false negative rate, false positive rate, and so the horizontal will be the false positive rate and the vertical will be the true positive rate. And I believe I have a chart to show you. So it is a way to choose a threshold that maximizes the trade-off between the two. Okay, if you remember from our discussion earlier about the potential output of a classification, it can be the direct probability or it can be the discrete category of the class, the discrete outcome of so the prediction can be one of the two. If it is a probability and you can pick a threshold value to optimize those two metrics, the sensitivity and the specificity. In the example that we use, for instance, if a model for the same email, if two models report that the probability of the same instance as 0.51 and another 1.95, the confidence you have in the two outcomes different, right? For the true case, you tend to believe the model that has higher confidence, higher probability reporting. But in some instances, a very low number can be leveraged or can be used in the interest of optimizing the sensitivity and the specificity. So a ROC curve is a way to find that optimal threshold value. Okay. For some applications, the default value of 0.5, anything above 0.5 will be classified as the category of interest. or in some cases, I have seen application where point 1 might be sufficient to classify as a positive class or as a class of interest because of rarity of that event. Okay, so RAC is a way to help you find this optimal threshold. So it is created by evaluating the class probabilities across a continuum scale, right? So when you see a single chart, that's for a single threshold, okay? And for each candidate, the resulting sensitivity, and so the horizontal is 1 minus the specificity, and the vertical is the sensitivity, which is the true positive rate. They are plotted against each other. And here is one. Again, this is for one threshold. And I took this chart. I don't know exactly whether for the default value or not. So for one threshold, this is, so the horizontal line is a false positive rate, 1 minus specificity, and the vertical is a true positive rate. Okay, for one threshold, this is the performance of the model. For different values of the false positive rate, the corresponding true positive rate, just create a line. And you can compare that this diagonal line, which is a null model or the default, it's just a random guess, right? And so you want the RAC curve to look like something like here. You want it toward the top left corner of this box, the diagram here. Okay. Now, like I said, it will help you identify a threshold that maximizes the sensitivity and the specificity. And a very important parameter that goes with RAC curve is area under the curve. That means you calculate the area under the curve and you want to maximize that. So you pick a threshold value that increases the AUC. It's called AUC. Okay, so part of analyzing the RAC curve involves calculating the area under the curve. Again, like I said, the optimal model should be shifted toward the upper left corner of the plot. Something like now, if perfect model will have an AUC of 1, will be exactly for a very low point of the false positive rate. It just shoots up to the highest true positive rate, and it will be like this. And then the area under that will be 1, but rarely will you get like that, something like that. There's no perfect model. There's always uncertainty, noise in the data. And if you remember some of the discussion that we had for linear regression, sometimes the uncertainty is part of the data itself, right? You can't reduce it. So very, very rarely possible any that you would get a perfect model. So that is a RAC curve and area under and this is primarily for binary cases, but the extension for multi-class problems as well. Okay, here is an output for one model that I used for, it's irrelevant to what model, but this is 3 multi-class problems, 3 class problems. So you can actually generate confusion matrix for multi-class problems. Now, like I said, confusion matrix is not a metric by itself. It is a way to capture different matrices, right? And most R function, I think I use probably caret package here, but there are other packages, the ROCR package, the PROC package, and there are other packages that you can leverage to produce confusion matrix. Now, in addition to the actual table, this captures a number of cases. Now, I think most of them we already discussed, these different parameters. So here is a confusion matrix. Well, the reference is the ones that are the actual cases in the data. Again, you should do this both on the training and the test. You have to evaluate on both samples and compare the result of the two to safeguard. One way of safeguarding overfitting. So here is the prediction, the horizontal is prediction. So as you can see, this is a very good model because a large number of cases are captured on the diagonal, right? of the diagonal elements have smaller numbers. That means the wrong classification is relatively small. And that mimics the metric that you see here, the overall accuracy. If you remember, the overall accuracy, particularly if the data is balanced, is okay, which is the case here. More or less, we have very little imbalance in this data. So accuracy tells you 96 accurate, 96% accuracy, which is a good number. And then there is a corresponding confidence interval. So the 95 confidence interval, that the probability that will fall between the two range. The no information rate is a null model. If you don't fit any model, and if you take the class with a large number of cases and divided by the number of cases you have in the data, that is the number you get. So the no information is this. So that means the model is a lot better than random prediction, right? 96% versus 38%. And this is a corresponding p-value, and the kappa statistic, again, this is a measure of agreement between what is predicted and what is actual, and which is high number as well. And then this is one of the things that we discussed earlier, is if the data is balanced relatively, then the number kappa and the accuracy number, they tend to be close to each other, they're proportional to each other. And the corresponding p-value here, and then we discussed about p-values when we discussed linear regression in the last module. Okay, here are the other metrics that we discussed: sensitivity for each class. Well, those are binary measures, so you have to measure for each class, right? So for class 0, sensitivity, again, higher number, which aligns with the accuracy. Now, if you have imbalanced data, in general, you will have the accuracy could be higher with a corresponding a smaller number, either for the sensitivity or for the specificity. But that's not the case here, as you can see, that because we have relatively, the same number of cases, not quite, but relatively balanced distribution. So sensitivity and specificity for each class, because this is a 3-class problem, and then you see the positive prediction value. Remember, the one that involves the prevalence. Same for negative, the precision, the recall. These are the things that we discussed. The F1 score, this all reported by this package. Okay, the prevalence, the detection rate. This is the overall detection rate, not just for on a positive, but for both the positive and the negative. And the balanced accuracy is you perfectly balance the distribution. That means if you have exact number of cases for each class, this will be the matrix. And then, like I said, we have these output values for each of the classes. So that's confusion matrix. And I just want to reiterate what I said before. It's a very critical and important aspect of model training or fitting a model is spending enough time on setting the parameter, experimenting with different values of the parameters to make sure the performance that you see is what will be in the future. Okay, that is, the generalization error is accurate. Now, this is the part where in the exercise, this is the main difference between the exercises and the assignments in the class. In the assignment, I expect you to do, not elaborate to this level, but I want you to do experiment with different parameters, regardless of what kind of algorithm that we're covering in that particular module. This is not unique to any algorithm. So you have to experiment with different parameters, and you have to explain the performance of the model on independent tests. And I want you to talk about overfitting, and if there is an indication of overfitting or not. So this is really the critical aspect of model fitting performance evaluation is. Okay, cross-validation, that's the last topic that I'll be talking about here. If you remember earlier, you have to sometimes the data you have might not be sufficient. You might not afford to have a dedicated training in a dedicated test set. Okay, because when you do splitting, you have less of it, right? So cross-validation can be used for that case. So that's one application. Another case is, particularly when you are applying advanced algorithms, you don't know the parameters beforehand. You have to experiment. You don't know the different combination of parameters. There is one technique that I'm not getting into called hyperparameter search. It could be grid search, could be random search. That is a way to find some combination of parameter, because most non-trivial modeling involves a number of parameters. So as the number of parameters increases, and that's what makes neural networks a very difficult thing to train on, because number of parameters, that they're hyperparameters. You have to define the number of hidden layers, which we will cover in the module 4. So there are other ways of finding optimal parameter, right? But here, one other use case of cross-validation is to have to determine best initial values for your parameters. So you apply cross-validation based on the performance of the cross-validation. You start using those values. In some cases, for instance, trees, the number of trees for ensembles, you don't know how many trees might be sufficient, so you apply it on cross-validation. So what is cross-validation? It is an approach to create multiple independent training and testing samples and still use the entire data set for both modeling and evaluation, right? So very good thing. So I have my sample from a given domain. So in 5-fold cross-validation, there's always k-fold, right, in cross-validation. The most common one that most machine learning sciences and data science happen to use is 10-fold cross-validation. I don't know the theoretical justification for that, but it looks like from research to research, the 10-fold cross-validation performs well. But here I'm showing a 5-fold cross-validation. So you split the data into 5 items, 5 separate splits, right? And now you use 1-fold for testing the model performance, and you train the model on the rest of the data. Okay, so that's one model. And then you, in the next model, and then you do the training, you do the testing on the 2nd fold, and you use everything else for training the model, right? The key is you should not evaluate the model on the observation that contributed to the training. So by following this strategy, you're avoiding doing that. You're not performing. So you're using this for training and using the other one as independent set. And you keep doing by sliding the window here. Now the 3rd one will be the test, and the remaining for training, and the 4th one, and here the 5th one. So I'm performing the evaluation on the 5th one, and the rest will be training. Okay, so I have used the entire data set and evaluate the model performance on independent set without sacrificing anything, right? Without losing any model performance. So that's what cross-validation is. And in general, it's a very, very useful tool to evaluate models. Because if you think about it, if you just take one seed, and if you perform the test, because of sampling issues, sampling noise, the performance you get, your evaluation of the performance of the model might not be accurate. So you need at least a minimum. The cross-validation, the 5-fold cross-validation in this instance gives you different combination of cases, different possibility, right? Even if you don't decide to use cross-validation, at least I would recommend you use multiple set. That means just to make sure the consistency of the model from sampling to another sampling. Just make sure the performance you see is influenced by noise, random sampling noise. Another thing that I didn't talk about, when you do sampling, stratification is an important aspect of that, particularly when you have imbalanced data. So stratification is nothing but when you take random samples, you try to maintain the relative distribution frequency distribution of the different outcome of the class, right? So for instance, if you have, I don't know, 1,000 emails for identifying spam and non-spam, for when you select your training, you want to maintain the proportion of the negative and the positive sample in the sample that you are using for training. So that's called stratification. It's less of a problem. Stratification is less relevant when you have regression problem, when you have continuous target variable. But for classification, it's important to stratify the cases. Okay, and that is the end of this. We will have another lecture on decision trees, but this is related to classification basics and about the performance evaluation model. Okay, any question you might have, we will discuss in class. Thank you for listening.